So good morning, everyone. Welcome to this presentation called Runtime Hardware Acceleration of Neural Networks in Unreal Engine. During this presentation, we will be showing some of the works developed by Qualcomm Snapdragon Studios to make or to run AI models on devices using Unreal Engine. More precisely, we're going to be showing our own plugin developed to run inference using the Unreal tool to do so, which is the Neural Network Engine, or NNE. My name is Carlos Castellón. I am a senior software engineer in Qualcomm. I've been working on the game industry for about 15 years already as an AI and gameplay programmer. Before joining Qualcomm gaming division at the Snapdragon Studios. So to start with this presentation, I will show you the agenda for this presentation. First, before this, I'm going to make a quick introduction about Snapdragon Studios so you can understand what we do exactly. And then I'm going to start painting a picture of machine learning in gaming, all the applications that currently are using machine learning and potential areas where we can improve more or use more neural network models to find new ways to solve problems. Then we're going to see Qualcomm, what the offer from Qualcomm to run these machine learning models and more precisely how to run it on device. Then we're going to see the offer from Unreal Engine for machine learning. Next, we jump into to show you how we took Qualcomm tools and Unreal Engine tools and we unified them in our own plugin to run inference. In this point, the best way to show this is use an example. So we're going to try to follow a live example of how to easily take a model, bring it to Unreal, and run it on a mobile device. Finally, we're going to go through model optimization techniques, which is an important chapter when you are considering running models, AI models on mobile devices. At the end, I will give you some takeaways and some other resources if you want to continue studying this subject. So, to start our presentation, I want to present the Snapdragon Studios. We are a team or a group of multidisciplinary people. We have engineers, we have artists, we have designers, and our objective is create gaming technology to enable the best experience in gaming. We work in different business units. We have developments for mobile, for PC, for VR, and for auto, as most of you already know. Our AI group focuses on bringing machine learning models, AI models, into gaming. So we want to harness the power of Snapdragon power devices into gaming, basically. One of our first, not our first, our previous efforts was a game we developed called Air Derby Battle League. In this game, we had NPCs running entirely on machine learning models. The decision making was made by machine learning models instead of using like scripted AI like behavioral trees or state machines. Every decision was made by machine learning. And this game actually featured our first version of a plugin for Unreal to run inference on device, which showcases in 2022, in one of our tech summits. So this was the first effort, even before having a tool like NNE for Unreal. Now, with NNE, we are able to do examples like this. This is the hand tracking model, a very popular model that recognizes hands and is able to track different parts of the hand. We can do that with a few simple steps, very few instructions, because we now have NNE, which provides a way to do so. Actually, this is the demo we are we will be following in this presentation. This will be like our hello world for our plugin. So let's continue. First, well, before showing how to do that, I want to make a brief introduction of machine learning in gaming, paint a big picture because the field is pretty big. So this, with this slide, I want to present like the big world of machine learning in gaming, and I'm sure that most of you will see. Well, I run out of space because there are many applications where currently machine learning is being applied. For instance, in graphics, you had heard about AI upscaling, and or in animation, you have heard about motion matching, even done by machine learning. In content creation, I have plenty of examples. You have seen smart NPC characters controlled by LLMs, content generation with stable diffusion. But in QA is frequently used machine learning in player services for anti-cheat localization, content moderation. Machine learning is already used, but there are plenty other fields where machine learning can really produce like innovation. For instance, locomotion. Many of those fields are still, we still use scripted AI. Locomotion is one of those. Navigation, pathfinding, collision avoidance could benefit from machine learning or a neural network approach by producing more organic results, for instance. Decision-making is still a lot to improve. Physics simulation can free up resources from CPU, for instance. So there are many opportunities to continue innovating using neural networks. Now, why we should use or consider run those models on device? Where there are very evident benefits from running on device. One of those is latency. You have the model on your end device, on the user device, and you don't have to stream data back and forward to a cloud service. Reliability. Because of this, the model is always available. You don't depend on network to run inference. Privacy, obviously, the data keeps in the local device, in the local machine, and you don't have to incur in costs related to cloud computing, so the cost is another of the benefits. But for gaming, there are more interesting benefits that you can explore. One of those is personalized. This is like a crown jewel for gamers and game designers to be able to create tailored experience for each customer. You can use exclusively the player data to produce exclusive content for that single player. So let's think, for instance, you can have a neural network model scheduling tasks for the player, creating a quest or generating a quest for the player using only the player choice, the player level skill, the player playing style. So it's basically like having your game designer on your pocket. Also, you can explore creativity because right now there are more and more devices with neural processor capacity. So you can dare to explore new ways to solve gaming problems. Before we have a technical wall that prevents us to go into neural networks because it was very demanding on resources. But now that wall is getting off the way because now you have devices capable of doing so. So you can dare to be creative on your work. So with this, what are the options to run on device? Well, devices right now, you can run either on CPU, which has low latency because you're running on the same CPU, but the performance is not the best, but then you can jump into GPU, which is frequently used for neural network inference also. But there you will need to share that resource, especially in gaming. Now, there are more and more devices with a specialized core dedicated only to neural processing. So they have they are able to sustain like large workloads at low power. And also, if you run neural network process on the NPU, you free your CPU or GPU for other things, as you should. So Qualcomm is able to target any one of these ways to run models on devices. So let me show you now what is the software offer from Qualcomm to make that possible and pertinent for our implementation. The first one is the Qualcomm AI Stack, which is a family of software solutions to execute, optimize, validate, analyze AI models, harnessing the power of Snapdragon devices. There are different solutions here at different levels of abstraction, but the most important, the one that we use, is the Qualcomm Neural Processing SDK. Along my talk, I will refer to this tool as the Qualcomm SDK, to shorten it. Probably some of you already know it as SMPE, but I will refer to that as Qualcomm SDK. And this tool allows you to load and run models in any Qualcomm device. It uses its custom file format for the models, with an extension DLC. And the SDK takes care of the loading and the execution of the model for any target, so the developer doesn't have to concern about how it's loaded or which device is running it. So this is very convenient, because that proposes a simple way to load those models into any application. Let's think you have a training environment, could be TensorFlow, could be PyTorch, could be a TensorFlow-like model, Onyx model, and the SDK provides the tools to convert it into our own format, DLC, and you take that single format, load it into your application, and the application running the SDK is capable to deploy that model to CPU, GPU, or NPU. Since the process is that fast, you can easily iterate, take your model, retrain it, and integrate it again. That's one of the tools we use it. This is actually the library that we integrated into Unreal. The next one that we're going to use is the AI Hub, which provides an extensive collection of AI models for different applications, and those are already optimized to run on Qualcomm platforms. Also provides an API when you can have your custom model, put it into the platform, convert it, optimize it, run it, and profile it in a device on the cloud. And once you do that, you can download the model and run it on your local device. Actually, we will be taking our model from this platform. Now, on the Unreal Engine side, what are the AI solution or the proposed AI solution they have or we have on Epic? Well, it's simply called a Neural Network Engine, or NNE, which provides a common API to access various or different runtime engines to run neural network inference inside Unreal Engine. It's not highlighted here, but the keyword here is common API. That is important because it uses the same set of instructions to load the model and run the model, no matter the details of the implementation of the target platform. So you might have a Onyx runtime, you might have DirectML, you might have even our custom platform for Qualcomm devices, but you always use, the user always use the same set of instructions. That is very important, because that means that NNE is agnostic for the details of the implementation, which is pretty cool, and proposes five simple steps to load a model. You can load a model also from blueprints using the properties on an actor, for instance. But here I'm showing an example on C++. And you maybe recognize that those instructions, if you're familiar with Unreal's programming. There is an instruction to load the model, which you load the model as you load any asset on Unreal. NNE uses its own asset format, which is called model data. So it loads as any asset on Unreal. Then you get a runtime, and here there is an example of that single call it a runtime by name. This is the one for the Onyx runtime on CPU. Then you create the model and the instances of that model to actually run inference with a couple of simple instructions. You set the input. The purpose of this step is to reshape the model if you need to. And finally, you have that model ready to run with that single instruction, run sync. You might notice that here are a couple of variables, input, output, and those are NNE structs that had pointers into the input data and pointers into the output data. That is to prevent copy. So probably when you have your custom implementation, you will use certainly this set of instructions and some custom manipulation for the data. Is the only difference. So developers and manufacturers can create their own runtimes, as we did. Here, there is an example of different users of NNE. We have the ML deformer, we have learning agents, we have the denoiser, and those uses different runtime implementations which are provided via plugins. For instance, learning agent uses the custom CPU runtime, and we created our own plugin, our own implementation for Qualcomm Snapdragon devices, which implement the Qualcomm SDK. Here you will see some of the users. Example, probably you're familiar with the deformer and the learning agents example. And now, next, I will show you how we take with these two things, NNE and Qualcomm SDK, and we created our own plugin to run inference on mobile. First, I will make a brief introduction of how the implementation was made. NNE provides a series of interfaces to implement the runtime and the model. Here you see that our implementation inherits from CPU, but NNE provides different interfaces to run on CPU, to run on GPU, to run on inference on synchronized with the GPU pipeline. And from 5.5, there will be a new interface to run on NPU. By the time of this integration, the most similar for us was CPU, so we inherit from that one. We create our own class for the model. We create our own class for the model instance. And this one here is a factory class, which is an editor class that allows you to convert our DLC into model data. Basically, this allows you to drag and drop the DLC into the editor. We copied this from an example provided by NNE, which does the exact same thing with Onyx. Finally, there is a third-party library inside our plugin that contains all the library for the Qualcomm SDK. So basically, anyone who wants to make its own runtime, we have to probably do the exact same thing we did here. Now, the important thing is I want to show you how to use it. So how can you run models on Unreal for mobile devices? The first thing you need to do, well, you need two things to run this is obviously Qualcomm SDK, and the second thing, our plugin. So here I will show you how to do that setup in a few slides. The first thing is that you can do it in any project, but we will be using our hand tracking demo. And there is a repository where you can sync this project already, which is there. In this demo, we will be controlling with the hand a model and the tracking points of that model. So you download this model and sync this model, and you already have a project to start on. But as I mentioned, you can do it with any project. Next, you will need Qualcomm SDK. Qualcomm SDK can be retrieved in this address, and you can download it as a zip file, or we have provide also an installer. And the important thing here for the next step is take note of the path where you install it, the SDK, because you will need it. No worries, I will present a summarized step-by-step information of all this. Then you will need to download our plugin and install it in either on your project or on Unreal Engine as a project plugin or engine plugin. Our plugin is located in this repository as well. So here I'm showing an example how to add it as a project plugin. This is the hand tracking demo project. You simply drag and drop our plugin into the plugin directory, and that's it. But remember, there is a third-party libraries inside our plugin, which is the Qualcomm SDK, and you need to copy those libraries there. But we provide a batch file that will do this for you automatically. You just simply have to navigate to that path, which is located here. Plugins, SMP, source, third-party, SMPE library. And then you call this batch file, providing the directory into the Qualcomm SDK. And that will copy all the necessary libraries into your plugin. You just need to build your Visual Studio solution, compile, and you are ready to go. Ready to use models on Unreal. Now I want to show you how to run these models on Unreal, and let's go step by step from the moment you grab a model. In this case, how this model, we're gonna grab it from our Qualcomm AI Hub. So you go to Qualcomm AI Hub, you will see that here is the location of the media pipe hand detection. And Qualcomm AI Hub provides you the way to download it for different platforms. The one is of interest of this project is the landmark detector, which is the one who provides the points of the hand to track it. You choose the device for which you want to run the model. This is because it provides an optimized model for that device. And the format. We're gonna make our conversion from TensorFlow Lite to DLC, so we will download that file on TensorFlow Lite. You download the model, and then you will have a model to run with. You can add additional information from AI Hub about that model with more metrics that will give you information about the input of the model, the inference time, and some performance information, which is important. You might want to see. Next, the next thing you need to do is convert it, according to our workflow, is convert that model from TensorFlow Lite to our single file format, which is DLC. To do so, Qualcomm SDK provides the tools to that conversion. Those tools at this moment are available only on Linux environment. So if you don't have a Linux machine, you might want to install on your Windows machine WSL. And in this next slide, I will be providing you the steps to make that WSL, which is a virtual Linux machine on Windows. And Qualcomm SDK run perfectly on this. And you might want to make a setup or a configuration of Qualcomm SDK in that Linux environment. And these are the links for that. Later I will give you a list of the steps. So we do that already in this machine. And if you did all the steps, sorry, probably the font is a little bit small, but I explain what I'm doing here. If you do all those steps, you probably will have an environment on Linux with a virtual environment, of course, and you will have some environment variables already created to access all the set of tools to convert the model. So one of those instructions is actually this TensorFlow Lite to DLC converter, which is a single call. In that instruction, you provide an input network, which in this case is my media pipe hand detector. You provide the input dimension of the image and the output path, which is the DLC files. When it does that, you will have a conversion already done on your side. So you will have a model with DLC extension already to drag and drop into your Unreal. This file is completely compatible with Unreal Engine, and you can drag and drop it in your content, and it will be converted. It will be converted into data model. So you will see the data is already there in Unreal Engine, and you might see this. The information here says that this model is able to run on our runtime. Now from there, you can take that model and run it, load it and run it either from code or from blueprints. And I will show you how to do so on the blueprint case, on the C++ case. So for that, let me show you that the hand tracking model that we are using has a subsystem with all the necessary code already there. So if you want to browse it later, you will see that there is a hand tracking subsystem which has two functions, one initialize and one to run the model. The initialize will load the model and initialize the input and output buffers, and the process will actually call the inference for that model. So here, this is the actual code of that function. I will mention the important part. You will see that it's exactly the same set of instructions I mentioned before. You load the model as you load an asset in Unreal. You get the runtime, and notice that this time we are using our runtime SMPE, which is our runtime from Qualcomm. We validate if these two are valid, and once we do that, we can create the model, create one model instance, and set the dimensions of the input of that model. For our Qualcomm case, this instruction needs to be initialized with the exact same dimension or input dimension of our model. Next is you need to set all the input and output buffers. To do so, the most important part here I want you notice is this output bindings, input bindings. This is a destruct that had pointers into the actual input memory area, which is the pixels here I'm fitting, and this is the input, and the output to the output memory area, which is, since this model has 3 outputs, we had 3 arrays here to contain all the data from that model. And that is the initialization. Next thing is how I use it. In the process function here, I just call runsync, passing the input binding, the output binding, then I parse the output and make some manipulation here for visualization, and that's it. That is all the thing we need to do to run inference there. So, this is a new file. So if we want to see how this looks on Unreal Engine, we have this, our map. This already have the model already loaded. So we can run, this doesn't have a camera, but I managed to put it like an image. There will be some trackers trying to follow the hand there. And this is defaulted to CPU because this PC doesn't have an NPU. But when I run it on mobile device, it will use the NPU directly. So once you do that, you might compile your project or package your project for Android. If you package your project, it will produce an APK and batch file to load or to install your APK in your phone, and you can run it from there. So now I make a small parenthesis here. Always that you use our plugin, you might want to see if the plugin is enabled, and you should see it or make sure, especially if you integrated the plugin as an engine plugin. So once you do that, you package your project, you install it into your phone, you will be able actually to see it. Let's see if on your mobile. I pre-installed this later today, this same execution. So let's see if I can show you what this will do on your mobile. It will use your camera. I don't know, is it visible there? I can manipulate the points with my hand, runtime using the machine learning model I just installed. And these nodes, you can actually use them to control a control rig on your model. If you have a hand model, you might want to control the control rig. I make a small, you see I'm controlling the control rig attached to this hand with my model right now, real time, and the response is pretty much good. So basically, you went to a model graph from AI Hub, use NNE, use the same set of instructions you already know, and you load a model on your mobile device on the NPU. So with that, there is a question that you need to resolve. Right now, models are getting bigger and bigger. So you might want to optimize that model. Also, a smaller model runs faster and is more gentle on the battery life of your device, especially mobile devices where you are limited on battery, on power, and on memory. So you need to consider optimization. In order to consider optimization, I want to show you the set of techniques you might use. To optimize a model for this device, for mobile devices, you might consider quantization, which is decreasing the precision of the parameters of the model, pruning, which is eliminating redundant parameters, or knowledge distillation, which is training a smaller model with a larger one. Qualcomm SDK provides tools for quantization, so this is the one I want to display with more detail. And what does that mean? As I mentioned, it's reducing the precision of the model, so you will have a smaller model, a reduced size, which is better for the memory in memory-limited devices. Also, using a smaller precision, it produces faster processing and is more efficient on the battery. And there are different ways or different types to do this quantization. One is weight quantization, is reducing the precision of the weights of the neural networks inside, or activation quantization, which is reducing the precision of the activation functions. So usually you use a mix of two in different levels of precision. But also there is other classification of quantization depending on the technique you use to run the quantization. So you might have post-training quantization, which is applied after the model has been trained. With this, you provide a set of examples, of input examples to recalibrate the model. Or you can do quantization aware training, which is introducing the quantization while you train. Basically, the model learns the quantization. I will show you an example on how you can use Qualcomm SDK tools, because Qualcomm SDK tool has an instruction to run a quantization on the exact same model that I show you. So you might see that, here, the model, this model has 8 megs weight. This one, the one I want to transform, 8 megs. So I will use Qualcomm SDK to run a function which is called SMPE DLC quant. And you provide I'm provided the input DLC, a list of examples to use for calibration, provided via text, and the output path for the quantized model. So if I run that, it will run the model multiple times to calibrate. And once it's done, I can go back and see the new model here is 2 megs. It's reduced to 4 times the size. So that shows how important it is to quantize your model, to optimize your model. And I can show you some other examples that I took from the AI Hub. Remember, the AI Hub had profiling tools. So I run other profiling on quantization for different models. And you will see here that I have, this is the media pipe hand detection, the one that I just showed you, how it's reduced on size. You will see a slight reduction of the inference time. It's not that, this is particularly important when the model is a big model. You will say, but I have another example, is the Midas V2, which is for depth estimation. You see the reduction also almost 4 times the size. And here you can notice an important reduction on the inference time. This is the other example for the face detection, which is similar to the hand detection, but identifies some points on the face. Also, 4 times reduction and a slight reduction on inference time. The important here thing I want you to notice is that you will be having same as good as the original model, but with a smaller size. You see here I'm showing for this example that is provided by AI Hub. The peak signal to noise ratio, which measures the accuracy of how without going into details, how good is the model at detecting or doing his job, in this case, detecting faces. And usually that value should be higher than 30 decibels to say this model is working. See that the quantized and non-quantized version are both very high, 78 here and 51. That means that the quantized model works fine with just a smaller size. So that's why it's important for you to quantize when you consider running on mobile devices. With this pretty much conclude my presentation. I want to leave you with just a couple of things to think, takeaways. First, summary, I just show you our runtime, Qualcomm any runtime, to run inference on Snapdragon devices using Unreal. I show you our tools for conversion, optimization, execution, and profiling of machine learning models. Among these tools, we have the Qualcomm SDK and the AI Hub. I provided you the basis of quantization as a process to optimize models meant to run on devices. And finally, I want to leave you with these learning resources. All this hand tracking demo, I know I went pretty fast through it, but you will have a step-by-step tutorial in this address here. It's the exact same tutorial, step-by-step with more detail. Also, if you want to go into development or your own runtimes, I provide you the NNE access to that tutorial. And of course, the AI Hub, which I invite you to go, because there are plenty of models there, plenty of tools, and that can pick your brain as a game designer or as a game programmer or game developer. Finally, I want to leave you with an invitation to continue integrating on-device AI on your gaming projects. Not only migrating cloud AI into device execution, but also creating new ways to solve common gaming problems. You can explore your creativity here, maybe in audio, have a neural network dynamically creating and mixing your music with the intensity of the combat of your game, or creating an intelligent banter system that responds to the scene that is seen by your NPCs of your player. So I invite you to be creative and think of those new ways to solve gaming problems on your Unreal applications. With that, I will give you thank you. We had some time for some questions. And again, there are the links here for the ones who want to take it. Thank you very much.